the usual YouTube channel. Lectures will take place Mondays, Wednesdays, Fridays, and if there's any changes to be made, we'll come to that as we go along. 11th to 12. Plus, we're testing with load shedding, so sometimes the venue is not, and the recording doesn't quite work with the venue load shedding, not because there's no Wi-Fi or anything, but just because I can see it. So for those lectures, I apologize on behalf a priori. If I can do another lecture to cover that, then I will. Otherwise, there'll be gaps in the recordings. There may be times where we will have a lecture online. It will be in the usual spot, and I will do the online. We've done that last time. It's nice to do. But in general, this is the in-person lectures, and it will take place 11 to 12. I don't have any tutorial slots, because I don't have any formal tutorials, because it's not going to be a course where I tell you something, then I tweak something, and I give you something as a problem set, and then you convince yourself, you know, to perform a field theory. That's not how it works. This is, for many of you, probably, not for you, Dave, but for many of you, the last course that you will take before you embark on a research career. Right. So think of this course as a bridging between the traditional, I'll be back to the chapter problems and research problems. Right. So I'm going to give you problem sets. You're going to tackle those problem sets, and then we will mark one out of 5 problem sets that are coming away, but they're going to be non-trivial problems. Okay. And I want you guys to collaborate. Again, for those of you who did my differential geometry course last semester, you know how this works. I want you to work together. I want you to collaborate. But when you hand in something, I want it to be your own work. So even if you guys sit down in a group and you work together on the problems, when you write it down, you should understand what you're writing down. You should take, own what you're writing down. So if I ask you a question, in, for example, an oral exam at the end of the course, you should understand everything that you've written down. Much of the problem set in this will be to fill in some of the gaps that I'll leave in the lecture. So I'll make some statement, and the problem set will basically walk you through that statement. So it's going to be a very hands-on course, even more hands-on than the differential geometry, right? So while you certainly don't have to do all the problem sets, whether you like it or not, you can do some statistics, figure out which are the problems I will mark with you. It will be to your benefit to understand and fill in all the gaps that we're going to leave. I will try and make it as pedagogical as possible and try to fill in the gaps, but you really do learn by making mistakes and figuring out how things work. Rather than me just telling you how it works. Okay. There will be one final take-home exam, as we did in differential geometry. You remember all of a month ago. I'll have one final take-home exam. It will be similar to the differential geometry exam for those of you who did that. So it will be one long problem broken up into several bits. We'll work through all of those bits again. Same principle solved. You're welcome to collaborate, etc. But you're handing in your own work, and then this will be supplemented by an oral exam at the end. Right. Unless there are any objections to how that was done last time, and you'd like a 4-hour in-class exam, I think it worked out nicely. I think that you. Those of you who did this before learned a lot from that take-home exam. I want to structure it the same way. So you will work through a problem that will really teach you about a particular aspect of this. We're going to be covering quite a lot. And conformal field theory, even though it sounds like a very specialist topic, actually could go off in many different directions. It's because it's so important to so many different fields, right? And the reason, this is by way of motivation, the reason why I'm teaching you conformal field theory in a course that reads force and string theory is because string theory is a conformal field theory. And in fact, the leading proponents of string theory, the Montesquieu, the Newtons, the Ibergs, etc., that we consider the leaders in the field of string theory are all really just good quantum field theorists. So it's very difficult, and there was a time in the development of the sport where I felt like take students that had a background in differential equations, that knew how to solve a wave equation, and teach them this material. And it can be done, but then this goes down to very specialist route, and you get to learn something very, very focused, and you can jump into research problems. But it's really important to understand the foundations of the topic. And the foundation of the topic is quantum field theory. Not just any old quantum field theory, but formal quantum field theory. So we're going to be talking a lot about a class of quantum field theories that enjoy a very broad set of symmetries. Right? And that's what we're going to be exploring. And it turns out that all of these people that contributed to the field of string theory at its beginnings, to the first string revolution, to the second string revolution, all came from many different fields, and some of them left many different fields. So you may remember that either last year or the year before, the Nobel Prize in Physics went to somebody called Giorgio Parisi. Parisi started off as a string theorist who was working in the formal field theory and realized that a lot of what he was doing could be applicable to statistical physics. Not just any of statistical physics, he was studying spin glass, and that's what he got the Nobel Prize for. Okay. A lot of the development of string theory came hand in hand with the developments in conformal field. So I want to eventually get to one specific set of topics that is really quite topical at the moment, and this is the idea of what's called conformal bootstrap. Now, the bootstrap program goes back to before the time of quantum field theory. Quantum field theory by particle physics. It goes back to Berkeley and just post-Oppenheimer years in Berkeley, where the big push in understanding particle physics came from something called the S-matrix theory. And S-matrix theory was all about scattering particles and understanding the scattering properties. So there were a bunch of people that figured that if I just give you enough data from scattering experiments, then you can reconstruct the theory behind the scattering. So this was the S-matrix program, and it was what's called a bootstrap program. The idea is you can bootstrap the theory from the data. Right? So if I give you enough data, enough relevant data, could you use that to tell me what the background theory is? So this was a guy called Jeffrey Chu and his group, and that Berkeley group gave rise to some of the biggest proponents of quantum field theory and particle physics and string theory since David Gross, Stanley Mandelstam, they all came through this. Joe Wachowski, they all came through this particular way of thinking, and then Bootstrap died. And Bootstrap died because quantum field theory rose to prominence, where people realized that actually, you can write down a margin and an action for a particular symmetry group and use this together with the Feynman rules that we derive from this to compute all of the scattering averages. Okay. And then recently, in the last 15 years, I'd say, the Bootstrap program has been resurrected. And it's been resurrected because of two things, essentially. One is the idea that we have now the mathematical machinery to reconstruct these scattering amplitudes from the data. And two is developments in something called conformal bootstrap. To this, where the mathematical course would lead to the Ising model. Who cares about the Ising model? The Ising model is one of the canonical theories in all of this, like homoculture. Okay, it's basically a set of spins that can be up or down, 1, 2, 3 dimensions, etc. And the name of the game is to work out the properties of this theory of spins. In zero spatial dimensions, it's trivial enough that I can teach it in an honors course. In one dimension, I can teach it using integrals in that same honors course. In 2 dimensions, the Ising model is solvable. It's one of the handful of exactly solvable theories in physics. It was solved by a guy called Onsager. And it is, if you get a chance ever in your careers, pick up Onsager's 2 papers on the Ising model, and I'd say read it, but you still need a couple more years before you're there. But at least look at it. They are a tour de force of mathematics, right? Both of those papers, and they're worth just. Is one of the parametric. It's still not solved. So we understand it, we can solve it 0. Solve the mathematical, right? The closest we can get is precisely through this idea of the whole bootstrap. Okay, so this is the idea that if I give you some data, can I use that data? Can you use that data to tell me what the underlying theory is? So we'll be talking about this as we go on. So let me give you a quick outline of what it is I want to cover in this course. Where this is going. So I will start off at motivate why we would like to study of videos. And then I want to talk about the idea of conformal symmetry and symmetry underpinning these field theories. We'll spend a little bit of time talking about the conformal symmetry and how it works in relation to some of the symmetries that you're already familiar with, for example, the Lorentz symmetry. And then we're going to start off with classical theory. Quantizing. Now, you're already familiar with, done in the second year quantum mechanics, you're already familiar with some form of quantization. Right? Canonical quantization you would normally use is what's called equal time quantization. And it's based on a particular approach to doing it. I give you some space time, you take that space time and you split it up into a bunch of spatial sections, what's called foliation of space time. And then you use a Hamiltonian or time translation operator to translate you between those leaves of foliation of space time. And in equal time foliations, what happens is you select out time, the time coordinate, and you pick leaves that are perpendicular to that That's transport. On each leaf exists a Hilbert space, and as long as your time translation operator is implementing a symmetry in the system, then you can show using axiomatic quantum field theory that each of those Hilbert spaces are the same Hilbert space. Okay, that's great. That's for those of you that are doing the quantum field theory course. That is the quantization that you will be learning about. That is not the best quantization to apply to conformal field theories. Conformal field theories, what we do is instead of taking equal time slices, we take slices that are equal radius. So I take my spacetime and I foliate it not by flat surfaces propagating in time, but in spherical shells propagating outwards. This is what's called radial quantization. The reason for this is because we'll see that a fundamental property in conformal field theory is scaling. Okay, the ability to zoom in and out of my spacetime. So we will. I will also tell you about light quantization, which is another type of foliation, which will give us intuition for what happens in radial quantization. But in addition to this, I will tell you about something called the same operator correspondence, which will lead us to using operator methods in this quantization. Now, again, this is something that you are technically already familiar with to some extent. If you've taken, let's say, the harmonic oscillator and written it in terms of raising and annihilation, raising the lower operators, and studying the field using A daggers, that's the operator methods and that we will be talking about. But I will tell you about how we associate operators to states in the field. Okay. Then I will need to talk about conservation laws, because they're absolutely crucial to the definition of conformal field. In fact, one particular object, the spectrality tensor, will turn out to play a central role in this story. Right? So we'll talk about conservation laws, in particular Newton's theorem, a classical version of Newton's theorem, and then I'll tell you how we think about conservation laws and the associated symmetries quantum mechanically. So that will lead us to something called water identities. But I'm going to package all of that under the overall heading of conservation. Then we will need to do some representation theory. So this is the representation theory of the conformal group. Those of you who are familiar with the word, group theory, as you may know, is a mathematical theory that codes all of the stuff about symmetries. Okay, mathematics love the word group theory. Physicists not so much. Right? Physicists prefer, instead of working with the abstract notion of groups, to take those abstract notions and concretize them. Okay. The best concrete way of thinking about this problem that we know of is to use matrices. In other words, to map these problems of groups to vector spaces. This leads us to representations of the group. So we'll be talking about the representation theory of the conformal group also. Right. which will lead us to the idea of correlation functions. Now, this is the thing. In a calculus theory, there are lots of things you can calculate about it. And a lot of different quantities you can calculate. Energy, magnetization, various derivatives thereof, to lead you to things like sustainability and all that. In a quantum theory, the main observable that you care about are correlation functions. Okay. So when I said earlier that you can exactly solve two-dimensional Heisenberg, should have asked what do you mean? Right? What does it mean to exactly solve a theory? Do I write down the equations of motion and solve those equations of motion? Well, in the classical theory, sure, that's what I mean. I write down the equations of motion, I solve those equations of motion, like Newton's second law, for example, and that gives me some definite trajectory. In quantum theory, I don't have it because everything has to play by the rules of quantum physics, and one of those rules is Heisenberg's uncertainties. So what's left? Well, what's left are probabilities that you calculate for certain events to happen. Right? Those probabilities are derivatives. They come from deeper things. Those deeper things are these correlation functions, which tell you how certain components of your theory talk to each other. Okay? So these are the things that you can calculate. And if you want to give numbers, if you have experimental strength, and you want to give your experimental strength numbers to go calculate, to go look for things, you calculate correlation functions. You square those correlation functions, and then it gives you probability amplitudes. Okay, so this is what you should have learned from your undergraduate mechanics course. And they are the key things that you want to calculate in a theory, for example, in any quantum field. So when I said the Eisenberg model is completely solvable, what I meant is you calculate all the possible correlation functions that you ever want to know about the theory. If I give you some theory defined by some Hamiltonian set, right? And I ask you whether this theory is solvable or not. Your task would be to calculate all the possible correlations. Now, the reason why, one of the reasons why conformal field theory is so powerful is because back in the late 70s, early 80s, three Russians, Beloved, Polyakov, and Zamolodnikov, figured out that for conformal field theories in two dimensions, you can do precisely this. You calculate all the possible correlation functions, which means that you can solve any one of these guys. Right? So that's why these conformal field theories are so powerful, is that if you can map your problem to whatever problem you want to study, you can map your problem to a two-dimensional CFT, you can use BPZ and you can solve the problem. Right? And that's what people have been doing since then with a number of such theories. And then, because I think that it's important that we get our hands dirty and not just talk about these things in abstract, I'm going to be focusing on two classes of free field theories, and these are boson and fermions. So we'll look at a free boson and free fermion theory. And right up until here, this is pretty much a standard CFT course. Most CFT courses will cover this material at the very least. Then there are what I would consider two slightly more advanced topics that I would like to cover. Or three slightly more advanced topics, depending on how much time. The first one is what's called the operator product expansion. This is the idea that you can take two operators, multiply them in a CFT, and use the operator product expansion to write them out as a series expansion. And this was the foundation, realizing that this particular expansion took a particular form, what's called OBE blocks that led to the idea of the conformal bootstrap. And then again, depending on time, the last topic I want to cover is organizing model as a CFT. Okay. There's a huge amount of this last section, and a lot of it is very contemporary, let's say. So one of the things that at least this CFT has, and to some extent from Bootstrap and definitely the OBE has led to is the idea that what we thought of symmetries is a small part of the idea of symmetries on an order. Okay, so I'm going to write down how we think about symmetries in the second conservation course. And then if we get to this section here, I'll tell you about two new classes of symmetries that we've discovered only in the last 7 years or so, maybe eight years or so. This is the idea of generalized symmetries. The fact that what we think of as symmetries, as well as the associated things like Noether's theorem, are really what you would technically call, and again, this is in-house jargon for those of you who did my geometry course last semester, what we would call zero-form symmetries. They correspond to functions. Those functions are the charges that are available. Well, in the same way that zero forms are just a small subset of all possible p-dimensional forms, you can extend the idea of what are conserved charges from just charges, electric charges, magnetic charges, to higher form charges. So this is the idea of higher form symmetries, and in particular, we will touch upon the idea of non-invertible symmetries. Okay. So these are both topics that are completely current. In fact, I think this year's Chelsea Summer School focused on particularly these ideas of generalized symmetries. Okay, so hopefully we get to that point by the end of this. If not, I'm very happy to talk some more about these things. Any questions on your part? I realize I've been doing a lot of the talking. But anyway, anything logistics about the course, something you disagree with that you would like to cover, etc. Yes.
Sorry for the ask. For this course, we're going to be doing path interviews.
Yes, we will, and I'll tell you everything that you need to know about it. For one, and for two, I will put up my notes on the path integral. The notes that I would give out to the class last year, I'll put it up on Google so you have access to it. But you know, anything that we need, I will tell you about as we go, and then you can go to those notes and back that as you want. Those notes are very detailed, they cover everything from path integrals in quantum mechanics all the way through to 5-4 computing correlation function 5-4 here. Okay. They're not absolutely necessary for the course. You can take these to the face value, but when you get to the point where you want to calculate things, then it's useful to be. I'll put those ones up. Let me tell you about references. So there are a number of great references in CFTs that I'm sure you guys are ingenious enough to find them by yourself. But let me point you in specific direction. So the one that is absolutely all encompassing is called the yellow one. It's like this thick. It's just one of these Springer books, yellow. By Di Francesco, apologize for butchering the name. And it's called control field theory. Much of my notes are going to follow a set of lectures by Pauls. I think it's also called control field theory, or control field theory. And this is a set of lecture notes that you can find in the archive. And it's also geared up towards a more bootstrappy take on control field theory. There's a very good set of lectures that I saw. I haven't used, but I've gone through it and it looks pretty good. And I think it's called control field theory for particle physicists. I can't remember who the author is. So CFT for particle physics. Particle physics. If you haven't found any of these things, let me know and I'll give you the precise. And then there's a set of notes by forget the name right now, but it's called the control field theory on the plane. So this is that focuses specifically on two-dimensional control field. And then again, there's a number of different books that go into it in various details. The 2-volume set by Frankel of control field theory in various dimensions. That's absolutely exhaustive and exhausting. That focuses on specific aspects of control field theory. The one that I really like, that I recommend you use, at least as a reference, but also if you're trying to learn the material for the first time, is the first couple of chapters. It covers everything in quite a bit of detail. It does a lot of first quantized, second quantized quantum field theory, Wick's theorem, path integrals, etc. It's a bit heavy going, but it's worth the effort. Okay, so my notes come from a combination of this as well as from some lectures by Robert Koch. Again, Jacob will get all of my lectures, scan and upload them to uploading class. So you have access to my handouts. Okay. All right. So let's start off by asking the question: why conformal field? So conformal field theory is about quantum field theories that enjoy a particularly large symmetry group, and this is the idea of formal symmetries. I will expand on what this means just now, but by now, I hope I don't have to convince any of you that symmetries are useful in physics because they constrain the system. The more symmetries I have, the more constrained the system is. And the more constrained the system is, the easier it is to solve the system. So the first point to note was that symmetries constrain The more symmetries I have in the system, the more constrained the theory, the more likely I am to be able to solve the theory. And in a quantum theory, what I will always mean by solve the theory is be able to calculate all the possible correlation functions. Okay. There is an exception to this, which I don't know if you're familiar with this, but one of the great quantum field theorists in the 20th and 21st century, guy called Sidney Coleman, who was a professor of physics at Harvard, and really contributed enormous amounts to our understanding of quantum field theory. And Coleman had these legendary lectures. In fact, two sets of legendary lectures. One is called Aspects of Symmetry, and their blue book. This thing, and again, it's one of these things that I strongly, and in fact, if you want some another reference to go to Coleman's chapter on formal field theory, this aspect of symmetry is exceptional. But if you just want to learn about quantum field theory, aspects of symmetry is a good thing to go. So the aspects of symmetry lectures, that book stemmed from a series of lectures that he gave over many years at the everyday summer school. He also gave quantum field theory lectures at Harvard, and those are on video. And I'm pretty sure you can find them, but go looking for them. They are definitely worth the watch. If for no other reason than to watch a lecture chain smoking while he's lecturing quantum field theory. And Cole agreed, we'd like finish one, go straight on to the next. But Coleman starts off those lectures by exactly this statement. Symmetry is constrained physics. The more symmetries we have in a system, the easier the system becomes to solve. With one notable exception, going from non-relativistic physics to relativistic. Going from Galilean symmetries to a bigger set of symmetries or correct symmetries, actually the system becomes more difficult to solve. Okay? It's partly because it becomes so much richer than the non-relativistic. But as a general statement, symmetries constrain physics. The more symmetries we have around, the simpler the system is to actually solve. So you might think that something like for field theory, since conformal symmetry is such a large symmetry, in a sense that I will make this like now. You might think that it's a highly contrived system, that we're kind of making the system up just so that we can solve it, right? Make a straw man argument, make a simple enough system, you solve it, spherical power, and yes, you have a Nobel Prize. Actually, it turns out no. It turns out that CFTs, conformal field theories, are surprisingly universal. That is to say, they occur in many more places than we would think that they occur. They occur in high energy physics, like string theory. They occur in matter physics, like in theories of superconductivity, topological materials, etc. They occur in statistical physics, like the statistical physics of blocks, for example. So CFTs are a surprising large part of nature. The described by, or at least approximated by, conformal fields. As I said, there were statistical physics, there were matter physics, there were in high energy physics, and if you're interested in any of these topics, not just string theory, if you're interested in any of the topics that you know people are studying these days, in any of those disciplines, then understanding the mathematics and physics of field theories is a relevant thing for you to know. And I have to emphasize that it's not just physics, it's also mathematics. A lot of brand new mathematics has been discovered by the study of these conformal field theories, specifically in, for example, the Ising model. In fact, at least one, possibly two of last year's field medals were given for the mathematics underpinning the clean Ising model. Okay, so this is an extremely rich topic that goes way beyond just string theory. Before wading into the largely formal aspects of this course that I want to start off with discussing conformal symmetry, it will be useful for us to build a little bit of intuition and motivate this with some examples. And I want to use two examples here. One is the example of phase transitions in classical and quantum phase transitions in largely statistical systems, but also in thermodynamic systems. And the other one is a highly toy conformal field theory, which lives in 0 + 1 dimensions. This means that all the variables in this theory only depend on time. There's no spatial dependence at all. And before you write it off as a strictly toy model that's not worth your time, it turns out that there are actually physical systems that behave like this. In particular, set of systems called quantum dots, where you can take a bunch of electrons, for example, and confine them to very small spatial areas, so small that you can discard the spatial area at all. And then you have something that behaves like a generalized atom, if you want. So it has no spatial extent. Everything only depends on time. But it turns out that these quantum atoms, these quantum dots, are highly relevant in materials. Okay. So I want to talk about two examples. These are phase transitions. And conformal quantum mechanics. That will teach us a little bit about the general ideas that we're going to be working with without getting bogged down by the details. We'll come back to the details once we have some mathematical machinery to do that. But for the moment, you can get some idea of what it is we're talking about by studying these. So, the story begins with the entirely obvious observation that conformal field theories are quantum field theories that are invariant under conformal transformations. Okay. So now I should tell you what are conformal transformations. So conformal transformations are coordinate transformations that preserve angles between vectors. Okay. They might not preserve the length of the vector. So under this transformation, this coordinate transformation, the vector's length might change. But if I have two vectors, then that transformation, no matter what it does to the length of the vectors, preserves the angle between those vectors. So conformal transformations, CFTs, are QFTs that are invariant under conformal transformations. If it feels like I'm being vague here, I think deliberately so. I'm going to make some broad statements and then we're going to try and calm down on those statements to make them more precise. Okay, I think it's slightly better than if we go the other way around and start with formal definitions and then work our way out. Let's start with those on intuition and then we'll sharpen the intuition. So, conformal field theories or quantum field theories are very good conformal transformations. And conformal transformations are formal transformations that preserve the angle between vectors. So, conformal transformations are coordinate transformations that angle example. What do I mean by this? So let's go to something that we're familiar with, to vectors in two dimensions. So consider two vectors x and y. To be vectors in three dimensions. And so we have a three-dimensional coordinate system, and I've got two vectors, let's say x and y, like this. There's some angle that I define between these two vectors. Okay, and I can calculate this angle. I can calculate the angle between them. By calculating the cosine of the angle between them, and the cosine of the angle between them is the dot product of x and y divided by the magnitude of x and the magnitude of y. Okay, so this is something that you learn in first year already. Let me go here to go see it's 12 o'clock and the next class is get it. I'll tell you where we're going. First thing I would like to do is generalize this. I would like to generalize this notion of what the angle between two vectors are to two possibilities. One is higher than z dimensions, and two is possibly generally curved spaces or space times. Okay, so that's what we'll do on Friday. All right. Thank you. Scan them, take a picture of them, and then you'll have a file that you should upload